finite difference method, and I hope the finite difference method you understood pretty well. And I think you might have practiced the problem. I think yesterday Basak gave me the problem of the introduction method. I found that she did by hand, and even the quadratic convergence, the summation of fi square, summation of r square to the power half, and she was getting 10 to the power minus 2 minus 4 and all this other kind of things. So definitely Jacobian calculation and this type of computation is okay. Maybe what I can do that I may give one of this kind of problem in the exam, 2x2 system. Introduction method by hand. How long does it take for you to the introduction method by hand? 15 minutes. Okay. I assume 20 minutes. Okay. So one such problem maybe coming in the exam. Just by hand, you know how introduction method actually works. Okay. So today actually we are going to full lectures, and that's the end of the class. So today is our last meeting, and then we will meet in during the exam. So what I am going to cover today, the time dependent problem. We are going to cover time dependent problem. So what we have. So in our analytical method, we have seen Ax equals to B. This is the algebraic system. And this has been fully covered numerically. I think I have covered fully, whatever possible extent I can cover. Okay. And then we had the functional space. Why blackboard is so dirty? Functional space. We had system like dx dt equals to ax. That is the common for the vector space and functional space. Okay, this is a commonality. So any functional space, if you have ordinary differential equation, you can convert to dx equal to x and convert to the vector space problem. Okay, this is the problem, and then we have gone to the Ly equals to f, which could be d2y by dx square equals to f, or dou y dou t minus dou 2y by dou x square equals to f. Okay, this is the ODE, this is the PD. This is all covered in our. These are all for the syllabus. Nothing else I covered. Very simple. Algebraic system. Then you have a differential system which can be called as vector space problem, and we have the function pure functional space. You can get ODE and you can get PD. That's all. Numerically, we have covered this one. Numerically, we have covered this one. The portions we have not covered so far. These are two portions. So in this class, I will be trying to address this portion, and that's all for the syllabus. So this kind of system actually works well analytically if the linear system. That means if you have say dx1 dt, say 4x1 plus 3x2, dx2 dt equals to say 6x1 plus 7x2. But what will happen? If you put 4x square, 3x2 plus e to the power x1, x2, and if you have 6x1 plus 7x2 cube, e to the power sine x1. This is highly nonlinear system. You cannot solve by the technique because the matrix A will not be a constant matrix. Matrix A will not be a constant matrix. And in that case, the system is nonlinear. The system is nonlinear. Now, whatever things we have learned, it won't work. Whatever we have learned, it won't work. So, what we have to do, this type of system, if you want to solve, of course, we put a lot of stability analysis and all those things. I don't want to discuss here. That will be the higher level and mathematical techniques. But numerically, you can solve this kind of problem. And these techniques are known as time integration. These techniques are known as time integration. Okay, and what we will be discussing in this class? Explicit method and implicit method, and finally we will combine them and we will have something called semi-implicit method. So explicit, implicit, semi-implicit method. Their techniques we will actually cover. Okay, let's discuss what I am going to address. address. So when you have dy dt equals to f of y, this is the autonomous system or autonomous system? This is the autonomous system or autonomous system? Auto or non-auto? Autonomous system itself. Autonomous system. You can have autonomous system also. So you have a system. This function of y could be very complicated function. Could be say sin y e to the power y and anything. Could be very complicated function. Okay? You cannot integrate, you cannot get y. And this kind of equation needs only one condition, y is 0, which is initial condition. And this type of problem is known as IVP, initial value problem. Whether the finite difference method is called as VVP, boundary value problem, because both the boundaries have to be specified. Both the boundaries have to be specified. Okay? So, for the finite difference method, they are called as boundary value problems. Both the boundary conditions, the end points have to be specified. But for this type of problem, first order differential equation, only one condition is required for to get a unique solution. Finite difference method you need last class, last two classes, it was the second order differential equation. You needed two conditions. And generally speaking, the boundaries are generally specified. Sometimes boundary condition will not be specified because other equal boundary is not known, but the actually equal to 0 two conditions are specified. So in that case, it's possible to convert a BVP to IVP. But IVP problem, IVP is such that an initial point condition is known, the solution is propagating from the initial condition. Solution will propagate from the initial condition. So that is called as IVP. So generally this type of problems are known as initial value problem, IVP. Generally this kind of problems are known as IVP or initial value problem. Okay, so we have to solve by numerical. So what we have to do, so basically like finite difference method, so if you have t and you have y, so we can have t0, t1, t2, tn plus 1. So this time we discretize as delta t step. Each step delta t. Each step is delta t. Each step is delta t. And then how to get the formula? Our Taylor series is there. Numerical techniques advantage is there. There are two kinds of things. Ax equals to b. You know that matrix algebraic system that will do operation or integrated technique, and the functional space problem based on Taylor series. These are two things you have to know for the numerical technique. So that's why respectively straightforward. So in numerical technique, what you can do? Yt plus t delta t. What you can write? Taylor series equals to yt plus delta t dy dt at t. Am I correct? Order of error is delta t square. So you can write this as yt plus delta t minus yt divided by delta t dy dt at t. Order of error is delta t. Same thing what we have done. So one can write this as, if you want to have the n plus 1 in simulation equals to yn plus n plus 1 step, if you want to have the values equals to yn plus delta t into dy by dt is nothing but f1. So it is nothing but f of yn because at t. Order of error is delta t. So this you can see that right hand side, left hand side is unknown, yn plus 1. For example, we are going for the first step. y0 plus delta t f of y0. y0 is known. y0 equals to y0 is known. It's the initial condition. y0 is known. If you put the function at y equals to y0, this also will be known. So y1 will be obtained. If you want to obtain y2, y2 equals to y1 plus delta t y1. y1 is obtained here, you get y2. That means right hand side everything is explicit. Everything is explicitly known. Right hand side everything is explicitly known. You don't require to solve the system. Everything is known. You have to just go on evolution of time. You put the value, get the answer, put the value, get the answer. You no need to solve this problem. No need to solve, everything is known explicitly. So this method is known as explicit Euler method. This method is known as explicit Euler method. This method is known as explicit Euler method. And this method is easy to implement. And the point is, what I am going to discuss, quantitative, no, I won't go into mathematical details because we don't have time for all those things in class. For example, if you have dy dt equals to minus 1, what you get? Analytical solution? Can you tell me? Quickly, dy dt equals to minus 1. All of you know analytical solution. C to the power minus 1. Yes. How we can look like? Minus t. Yes, how it look like? This is the model problem you can take to test your algorithm. For example, you want to solve, you want to see how it is going on. You take this kind of problem. You give y0 equals to say 1. So in that case, your c equals to 1. Your solution is e to the power minus t. This problem given. I'm given to you. You can check this problem. Now, what actually happens? If your delta t is too large, your solution may go, numerical solution may go something like that, and which is called as numerically unstable solution. Numerically unstable solution. And you can always this. Numerically, if you take delta t, for example, 0.5. 1.5, such a usual maybe 1 delta t or 2. You can have any delta t. And you plot it out in MATLAB. You go back home and do it. Very simple. It will just take 1 second each step. You say high delta t, this will be just oscillating. So that means it has got stability problem, numerical stability problem. Although this method is very easy to implement, it has issues, serious issues of numerical instability. In that case, you need to have very small delta t. Otherwise, you can get numerical unstable problem. That means what? Explicit method is easy to implement, but it is conditionally stable. Explicit method is easy to implement, but it is conditionally stable. Explicit method is easy to implement, but it is conditionally stable. And if I offer any advanced numerical course, in that case you can see it will be possible to derive the stability angle of what. In that case, based on the stability analysis, it is possible to have delta t critical. Delta t critical for which you can get. So stability, a stable solution means what? This is an analytical solution. A stable solution which is oscillate, and then you can get this kind of solution. Numerically may not be always exact, but it should be matching the analytical solution. Right? So this is the numerical stable solution. And there is some special delta t, critical delta t. Initially my point is that here the gradient is very high. At this point you have very small delta t. Beyond that point you can have much better, no problem, much bigger delta t. But here if you have bigger delta t, you can get huge numerical oscillation, and once oscillation is there, it will not die out. It will propagate, and that's it. If you won't get the converse solution, you will get much error. And this is a very good experiment. If you want, you can go to your computer, do the MATLAB simulation, and you can see how a simple problem like this can lead to numerical oscillation and numerical unstable solution. Right? Okay, so we have seen that explicit method is easy to implement, unstable. You need to have very small delta t to have the stable algorithm. Next is implicit method. So this method is called as Euler explicit method, explicit Euler method. Next we will be going for implicit Euler method. Implicit means things are not known explicitly. Simple. What is implicit? Simple thing is not explicit. That's why it is implicit. It is not explicit. That's the way I explain it. It is not explicit. So what we can do here, we can write yt equals to yt plus delta t. I am doing t plus delta t as reference of what? Taylor series. Like fx equal to, I am writing fx plus delta x. What will be delta x? Minus delta x, right? H is minus delta x. So what will be the next step? Minus delta t dy dt at t plus delta t, order of error is, got it? Yes or no? What you got finally? Yt minus yt plus delta t by delta t equals to minus dy dt at t plus delta t, order delta t. One more step. Yt plus delta t minus yt by delta t equals to dy dt at t plus delta t. Am I correct so far? Yes or no? So what algorithm you get from here? Similar algorithm you can get. Can you tell me the algorithm for implicit order method? Can you tell me the algorithm? Can you tell me the algorithm? Can you tell me the algorithm? Yes or no? Yn plus 1 equals to Yn plus 1 equals to Yn plus delta t function of. Excellent. That's it. You derive the implicit Euler method. This is called as backward Euler method. This is called as backward Euler method, implicit Euler method. Implicit Euler method or backward Euler method. This is called implicit Euler method or backward Euler method. Okay, backward Euler method. Okay, excellent. And what actually happens here? If you look at right hand side is not known. Right hand side is not known because f of yn plus 1, how do you know? So if you want to implement, for example, I am giving a problem. Now let's look at how to implement it. Dy dt equals to y square. Y t equals to 0 equals to 1. What's the ideal solution? I want to test this algorithm for this kind of problem. Dy dt equals to y square. Y at t equals to 0 equals to 1. What is that? What is my solution? Ideal solution. Y equals to minus 1 by 1 by 1 minus t. Why to put my 1 by 1 minus t? Right? Correct? 1 by 1 minus t. This is my ideal solution. This is my ideal solution. So you can scale your time such that t is always less than 1, but doesn't matter. You can go to the negative part. That is not an issue at all. I want to implement implicit Euler method for this. Delta t equals to y1. How to do the calculation? y1 equals to y0 plus delta t f of y1. That means y1 equals to 1 plus y1. f of y1 is y1 square. Right? My first step is correct so far. I have not got y1 though. I know y0. My y0 is what? 1. Right? So if you look at, you need to solve this problem. How to solve it? Newton-Raphson method. To solve this, Newton-Raphson method. How to do that? We can y1, which is y1 minus 1 minus 0.1 y square. F prime y1 equals to 1 minus 0, 0.2 into y. Am I correct? So you have to get y1 new equals to y1 old minus f of y1 old f prime y1 old. What will my guess for y1 old? First guess, y0 converse solution, which is 1. There's a best guess you can get. The best guess, similarly, if I get y2 old, it will be y1 converse solution. If it is y3 old, y1, y2 converse solution. So that way, this previous time steps converse solution will be taken as the initial guess. So what you will get? So y1 new equals y1 old is 1. F of y1 old is, if you do point y1 square is, what is y? Yeah. F of y1 will be, f of y1 will be, not f of y1 is not pointed, y1 is 1. 1. This is my fy, come on. This is my f of y. f1 is 1, that's 0, right? Am I correct? Yes or no? Yes? Okay, oh sorry. Okay, I think this slight confusion. See, if you don't have the proper symbol, even I am also doing mistake. Capital F. This is my small f. Don't put small f here because in that case you do mistakes. I was doing mistake. Capital F. Can you put it? Capital F. Okay. F of y1 old is y1 equals to 1. 0. Minus 0.1, am I correct? This is 1 minus 0.2 into 1, 0.8. How much it is? 1.25. y1 new again. 1.125 minus f of 1.125 divided by f prime of 1.125. Give me the answer. F of 1.125 is minus. What is that? Total, you are giving the complete answer here, no problem. If you give the full answer, I am with you. Only thing you have to give me correctly. You should have your calculator handy. You should have your calculator handy. You should have your calculator because this kind of problem will be coming in the exam and you will score very well if you can get very easy part. Whatever I am teaching is all easy part. Huh? 1. See how it is getting converts. y1 new. Again 1.127 minus f of 1.127 by f prime of 1.127. Give me quick. How much you are getting? Wow, excellent. So what you can do here, you can actually calculate every step. Summation of f I square, of course I equals to 1 to 1 square root, and see how it is converted. Can you tell me the calculation here? We will check whether you are getting quadratic converters. How much it is? Capital Fi, sorry. Again I am doing the mistake. Capital Fi square. What is that? 3 point. Minus? You are getting order by minus 3. What is your order? Minus 3? No, it will be minus 3. It will be more. Because see, this is getting difference, right? See, what are you getting? See, this actually, here you are doing f of 1.125 square root. Here you will be doing f of square 1.127. They cannot be equal. the parameter. Or somebody can calculate for the one-dimensional problem. I can tell you that even if you calculate f of x is okay, because both are same. Root of x square is x on. But it is by vector, definitely you have to have square root of x1 square plus x2 square, or square root of x1 square plus x2 square. But it's only one function is okay, no problem. This one function is okay. You can calculate function of x, that will be fine. Just calculate function of x for one function. How much it is? How much these values are? Any ideas? Pardon? How much the order of error? Simple thing I am asking. Function of 1.125. You can't get the answer. It is a for small f. I am sorry. This should be f. I think capital F only. Capital F. Correct. Pardon? Order is? Next one is? Yes, that's what I'm saying. Almost like quadratic. That's what I'm saying. It has to be. Otherwise, a problem. So you got the solution. So next step will be what? y2 equals to y1 plus. Remember that delta t small f y1. We don't put capital F here. Small f. Next iteration. Right? y1 is how much? 1.127. Am I correct? Delta t 2.1. f of y1 is f of y2, which is 0.1 into y2 square. Do the same thing again. So that is the way the entire implicit order method is actually being done for the computation purpose. And advantage of implicit order method is this method works better than explicit order method. This method requires less delta t. This method requires less delta t to convert. So numerically this method is more stable. This method requires more smaller. This method even works with a bigger delta t compared to explicit order method. This method works even with a bigger delta t compared to explicit order method. Numerically this algorithm is more stable than explicit order method. Only problem for this method is this method is difficult to implement because of the substitution. More computation expensive. That means we spend more in computation, but you get more stable algorithm. You get more stable algorithm. So this method is computationally expensive, although, but this method is more stable compared to explicit order method. Funda is clear? Okay. Next we will be going to the method which is the sort of multi-step algorithm. We will be talking about now something called multi-step method. Okay, before going to that, I forgot one thing. If I have sin y plus e to the power y to the power cos y to the power log y, this whole root of 1 by n, how to solve by implicit order method? If you take derivative, you will do mistake. Even I do mistake. Forget about you. I can give 100% guarantee. If I do from f prime y, I do mistake. I don't know. Maybe you are better than me. I will definitely do mistake and I will get 0. No part marking. If the teacher doesn't give part mark, definitely I will get 0 because I will do mistakes f prime. In that case, how I will come up? I have to calculate f prime correctly. This is a very difficult function. I will do mistake. I don't know, you may be doing better than me, you may be doing correctly, but I will do mistake. How to do f prime correctly? Any idea? So something called numerical Jacobian method. What does it mean? Numerical Jacobian method means if a function is very complicated. Sometimes what actually happens, your stochastic process. What actually happens? You give input, you get output. You can either digital blocks. You give some disturbance to the variable, like control, digital control. People working on the control, right? People working on the control, digital controller. You give, you get output. You don't know how the function. These are empty. How how to do implicit order method for this process. But the here function is known. I will say some function dy dt is some function. Question mark. Double question mark. What function you don't know? How to implement y1 equals to y0 plus delta t f of y1. When you solve it, you need to solve by introduction. Right. So in that case, numerical Jacobian method is very powerful. What it does, even if you don't know a function, even if you don't know how to take derivative, the function is very, very complicated. In that case, it is possible to calculate the derivative. How it will be done? If you have df by dt or dy by dt, you always write limit delta into 0 yt plus delta t minus yt by t. Remember the delta t is tending to 0, very small. We will capture this information. For example, I will take up this problem. F of y1. What is that? y1 minus, can you tell me? I deleted everything. 1 minus y1 minus 1 0.1 into y1 square. Am I correct? Okay. You want to find out the derivative a prime 1.125. Right? Here. This one. By numerical Jacobian. What do? You write f of 1.125 plus epsilon minus f of 1.125 plus epsilon divided by epsilon. That means here what I will do, I will like say epsilon is maybe 10 to the power minus 1. But my experience wise minus 3 will work also fine. Is your luck. So instead of having 8.125 you can estimate from here. You put 1.125 plus 10 to the minus 3, put it here. You get the value. Divided by 10 to the minus 3. You get the value. So that is the way, even if you have stochastic process, what you do is put 1.125. You get the function. You slightly plot up the input parameter. 1.125 plus 10 to the minus 3. You get the function. Subtract, divide by 10 to the minus 3, get derivative. No need to know what is common derivative. So I go by this method. Only thing is if you do numerical Jacobian method, Newton-Raphson method, will not converge quadratically. So convergence will be linear and slow because we are approximating the derivative. Remember that derivative is the direction of convergence. If you approximate the direction, Newton-Raphson method works this way. This is the way we draw the tangent. What does it mean? It is saying that you go this way, you get convergence. That means if you slightly change the direction, you will get convergence very slow. For example, you can go this way also. Then again you draw the thing. You go again this way also. Draw the thing. You take more steps. So this guy is a derivative or Jacobian. It is saying that it is the way I can go and get the convergence, right? So if you don't have the proper direction, speed is slower. That's what I am saying. What will it is faster? Minus 2, minus 4. The speed is slow means minus 2, minus 2, minus 2, minus 3, minus 3, minus 4. Convergence is slower. But you get convergence. Okay? Sometimes what I should have you writing computer program. You are putting numerical the derivative part in the Newton-Raphson method wrongly. Many people do in the exam or many people write the computer program wrongly. They will not get quadratic convergence, but solution is correct. That means in Newton-Raphson method, x nu equals to x over minus f of x over by f prime x over. You are putting this thing correctly. You may do something wrong here. If it is not too much wrong, you get convergence one day. Maybe it takes 10 days, you will get convergence. But if this is wrong, you get wrong solution. So this does not matter. It gives the direction of convergence. So if you have numerical Jacobian or numerical derivative, you may not have the proper direction. You are slightly disturbed. That's okay. You get to slow convergence, but still you can get a convergence solution. So that's the way you have got complicated function. You should not worry about. You go for numerical Jacobian, get the solution. Okay. For example, you have catalytic you have got reaction. Langmuir principle kinetics. Kinetics equation is very, very complicated. Remember that if you want to take Jacobian for that, it will be even more complicated. In that case, for that what I do, if you refer to my paper on chemical reaction engineering and microwave, I have papers. One paper in energy journal, another paper is AICT journal. If you refer to two papers, the reaction part, I did by numerical Jacobian approach. You can refer to my paper in 2010, 11, 12, I don't know exactly the one then you will find that. Okay, so let's go to another interesting aspect, which is called as multi-step method. So the multi-step method, what does it mean? This is my Tn, this is my Tn plus 1. Earlier you are seeing that at the Tn plus 1, you are getting solution based on information of Tn. At the information of Tn or Tn plus 1. In explicit method, everything is known here. Every explicit method, Yn plus 1 is expressed whatever is available in the backward direction. And backward direction and direction, everything is known. That's why explicit method is very easy. Implicit method, what actually happened? Yn plus 1 is expressed in terms of Yn and Yn plus 1 in terms of solution. But still, you are using these 2 points. Still you are using these 2 points. Sometimes you will say, no, I want to have intermediate information. To get better convergence. So, these intermediate steps sometimes give better convergence. And 2 methods we are going to discuss here. One is Crank-Nicolson method. Crank-Nicolson method. Another is Runge-Gupta method. Another is Runge-Gupta method, RK. So I will first talk about CN and then RK. First I will talk about CN, Crank-Nicolson, and then Runge-Gupta method. Okay, so what I am trying to say that I want to have some information in between. Okay, these are my tiny steps, but I want to split in between. Some people actually call this as operator splitting method, but I am not going to discuss all those things. In petroleum refinery engineering problem, this kind of operator splitting is very, very important. In fact, when I was working in University of Houston, Texas, and atmospheric science project, then I was involved in the operator splitting approaches. For time being, we should not talk about that. Okay, how Crank-Nicolson method works? So you are seeing that we are having Tn plus 1 by 2. We are having Tn plus 1 2. So we can actually have Taylor series of Yn plus 1 with respect to this, Yn with respect to this. Remember that Tn plus half is a point we don't know anything on intermediate. Okay, and then eventually you have to express everything in terms of Yn plus Yn, because intermediate point you don't have information. You are actually using, you are splitting further to get better convergence. We will show you that if you split here, how you can get better convergence. Let's look at that. Yn plus half plus, you tell me, delta T by 2, yes, dy dt at T equals to n plus half. Order, you can write delta T by 2 square by 2 factorial d2y by dt square n plus half. Order delta T. Why I am writing it, we will show you later. I am just setting one extra term. If you want, if you have questions, you have some patience, I will discuss. Yn equals to Yn plus half minus delta T by 2. Am I correct? Like that thing you have done in this method. Dy dt at n plus half plus delta T by 2 whole square by 2 factorial d2y by dt square n plus half order delta dt. We want to obtain dy dt. That means we have to subtract, right? What actually happens? This will get cancelled. That's what we want because we don't know yn plus half. Our midpoint is what? We are getting T0, T1, T2, T3. We don't know T2.5. We don't know T1.5. We don't know T3.5. That's what is happening. So these things have to be also eliminated. If it is not, it is a problem. We don't know how to eliminate it. Okay. So yn plus 1 minus yn equals to what will happen? Delta t dy dt at n plus half. Then the order of error, if you look at this, also get cancelled. So next term you contribute the error, and the error is order delta t to the power q. And then next step, yn plus 1 minus yn by delta t dy dt n plus half order delta t square. Right? How to evaluate this dy dt at n plus half? How to evaluate this? dy dt at n plus half is nothing but function yn plus half. We don't know this because what I said, this is the evaluation. This T0, T1, T2, T3, T4. You know Y0, you know Y1, Y2, Y3. You know Tn, Yn. In between, no, we don't know. That's the thing which will happen. We don't know. How to evaluate? Can you do the same thing in the Taylor series and get some kind of form for yn plus 1? This function of y, right? We can do Taylor series, right? So, function of y n plus 1 is known. Function of y n plus half is also known. So, can we express function of y n plus half in this kind of fashion? Can you do that? By Taylor series? Answer is yes. Can we expand Taylor series of f of yn plus 1 with respect to yn plus half and f of yn plus half f of and then do the f of sorry, it should be is what I wanted to say is not known. Please correct it. F of n plus is known, f of n is also known, f of n plus is not known. Because sometimes what I say and what I write not synchronized. So I have to be very careful. Okay, how to do that? F of yn, we can write f of yn plus half. Then next step, Taylor series. Everything Taylor series numerical analysis for the functional form. Not delta t, function of y, remember the delta y should be. No delta t. This t there, t is not there. Delta y. Delta y, then df dy, am I correct? At n plus half. Am I correct? Order f of plus or minus, this will be delta by 2, right? Am I correct so far? If I add, what will happen? F of yn plus half equals to half of f of yn plus 1. What's the order of error? H square only. You can see that same approximation. You got delta t square here, delta y square. Same approximation. Order of magnitude is okay. But one good thing is that it will be no more n plus half. It will be f of yn plus f of yn plus 1 into 0.5. Okay. So my algorithm is now yn plus 1 equals to yn plus half f of yn plus f of yn plus 1. Advantage is error of order of approximation, convert this delta t square, you get much better accuracy, and this is called as semi-implicit method. And one of the advantages is unconditionally stable. All computations are done by this approach. We always use Canty-Gaussian method, which is basically unconditionally stable. Which is basically unconditionally stable, and it gives better approximation. You can see that this order is delta t square. Order is delta t square. Any question? So this is the first simple multi-step method. You see that you have n plus half, you split between two time steps, you got the information, and you got the better approximation. Okay. So this is the way, this method should be known before Lange-Gupta method. So Lange-Gupta method is extension of that. Lange-Gupta method, what we do, in between two time steps, we have many such functional operations. So now we'll extend our idea for the Lange-Gupta method. So let's talk about Lange-Gupta method. And Lange-Gupta method I will be talking in a non-autonomous system, more generalized, so that you can actually apply for your research projects. Any question in doubt so far? Any question in doubt so far? Okay. So let's talk about now Lange-Gupta method. What's actually happening, madam? No, you are laughing, I saw that. I don't know. If you do like this, I don't know. How will you have success in your life? I am a bad person, I know that. It gets disturbed. You know, I take pain when I teach in the class. I don't know whether you want to become a professor or not. Of course not. This profession is a very bad profession. You get always mark from the students. Mark, insult, whatever. I am getting from you also. I have seen. You do all those things. You are doing research, right? Okay. I wish you all the best in research. I want to see you a good researcher by this kind of attitude. That will be a great achievement. Then I tell my students, be like I refer your case only. So Lange-Gupta method, what actually we do, we have Tn, we have Tn plus 1, and we can actually have in between so many functional operations. In between so many functions. So it is actually really multi-step. So our thing is that we are actually having T0, T1, T2 and so on, and in between we use so many steps, sub-steps. Why? To get better approximation. We saw order of delta t square. Can you have order of delta t cube? Delta to the power 4? Yes. Answer is RK family. Lange-Gupta family. So let's discuss how to extend that technique. To the Lange-Gupta method. I am sure this is the way it will be never taught in your college. You have done BTech, right? Nobody taught you. Now you understand why they didn't teach you. Because we are not interested. That's why they should not teach. I go to a private college and tell them there is no point to teach. I am teaching because I am stupid guy. There is no point to teach because I know that out of this class only 5 guys will do well, maximum. Others will get very bad grade. Of course, one my achievement is I am there with the 5 people, not for you guys. Okay, so what actually I will take up one example problem here.